a quiet archive record. Tonight, we drift into a place where silence carries the story. There is nowhere to go, nothing to hold on to, only a slow pull into the void. A human life is a small span of time on Earth, but space turns small spans into meaningful distances when you measure them in the right units. In this record, we look at what a lifetime can realistically reach, what it could reach with near-future engineering, and what it might reach in the far edge of theory. We start close to home with the orbits, the moon, and the outer planets, then move outward into the deep cold between stars. We use the same question in each section. If you had one lifetime, what would you see with your own eyes? And what would only your instruments see? We also separate two different meanings of distance. One is the distance you travel through space as measured by people who stay behind. The other is the distance you experience if you travel near the speed of light. Tonight, we ask how far we could travel in space in a lifetime. A lifetime begins with the simplest kind of travel, moving around Earth. The first boundary is not distance, it is speed. A plane crosses an ocean in hours because the air is close and thick enough to push against, and because the energy cost is supported by a planet full of fuel and maintenance. Space travel begins in a different place. The price of leaving Earth is paid up front in a violent climb that spends most of its energy fighting gravity. If you want to know how far a person can travel in a lifetime, you start with a baseline. What have humans already done in the real world with real vehicles and real budgets? The farthest any human has traveled from Earth is not a distant planet. It is the moon. The Apollo astronauts reached a maximum distance of roughly 400,000 kilometers from Earth, and they did it in a matter of days. If you imagine that as a lifetime journey, it is a strange kind of comparison. The trip was short, the life support was complex, the risk was high, and the distance was both enormous and small, depending on the scale you use. The moon is a turning point because it is close enough to reach with chemical rockets, and far enough that you feel the emptiness. Earth becomes a sphere you can cover with a thumb. The time delay in radio is noticeable. You are no longer in the same place, even if you can return quickly. Beyond the moon, human travel has not yet gone, but machines have. Robotic probes have crossed the full solar system and entered interstellar space. They show us that distance is not only about time, it is about patience, reliability, and power. The solar system is arranged like a small city that happens to be made of vacuum and ice. The inner neighborhood is warmed by the sun. The outer neighborhood is colder and darker, but it is far from empty. If you want to travel far in one lifetime, the solar system is the first true test. The first step is to define what a lifetime means. If you choose 80 years, you get a clean number, but the details matter. A journey includes planning, launch windows, time spent accelerating, and time spent slowing down. If you are talking about human travel, you also need the time it takes to build the vehicle and train the crew. For this record, when we say a lifetime, we mean the span a person could reasonably live through and still have time to experience the journey. We also consider a second case, a lifetime measured in the traveler's frame if the ship moves close to the speed of light. With that in mind, the nearest targets are the planets. Even with present-day rockets, a human could reach Mars in months. A human could reach the asteroids. A human could spend years on long loops that swing by planets and gain speed through gravity assists. Gravity assists are one of the quiet tricks of space travel. A spacecraft can steal a tiny amount of a planet's orbital momentum. It swings behind the planet, and the planet's gravity redirects the spacecraft, adding speed in the direction of the planet's motion. The planet loses an immeasurably small amount of speed, and the spacecraft gains a meaningful amount. It is a free boost, but it comes with constraints. You must wait for the planet to be in the right place. You must accept a path that is set by geometry, not by desire. If you want to travel far, you must either accept slow paths or you must bring your own energy. Chemical rockets are powerful, but they burn quickly. Most chemical missions use short bursts, then coast. To go farther within a lifetime, you want sustained thrust, even if it is small. That is where electric propulsion enters the picture. Ion engines and Hall thrusters push gently but continuously. They can run for months or years if they have power. The thrust is low, but over time it adds up. For a human crew, sustained thrust changes the experience. It can provide artificial gravity if the acceleration is strong enough. It can shorten travel times and allow more flexible trajectories, but it requires large amounts of electrical power. In the inner solar system, solar panels can provide that power. Farther out, the sun grows dim. At Jupiter, sunlight is about 25 times weaker than at Earth. At Neptune, it is about 900 times weaker. Solar panels can still work, but they must be large, and they must survive cold and radiation. If you want to travel to the outer planets in a lifetime with a crew, you likely need nuclear power. A nuclear reactor can provide steady electricity for decades. It can drive electric engines, heat propellant, and support life support systems. The next question is distance. How far is far in the solar system? The Earth is 1 astronomical unit from the Sun. 1 astronomical unit is about 150 million kilometers. The orbit of Jupiter is about 5.2 astronomical units. Saturn is about 9.5. Uranus about 19. Neptune about 30. The Kuiper Belt extends beyond that, and the inner edge of the Oort cloud may begin thousands of astronomical units away. If you travel at the speeds of present-day probes, you can cross the solar system in a decade or two. Voyager 1 and Voyager 2 were launched in 1977. They used gravity assists to reach high speeds. Voyager 1 is now more than 160 astronomical units from the Sun. It has traveled that far in under 50 years. That sounds like a lifetime scale journey, and in a way it is. But the Voyagers did not carry people. They carried small instruments. They carried radio transmitters powered by radioactive heat sources that slowly weaken. A human crew changes everything. You need air, water, food, radiation shielding, redundancy, and comfort. You need systems that can be repaired with limited parts. You need a way to handle emergencies. You also need a reason. Still, if you imagine a human mission that does not aim for another star, the outer solar system is a plausible lifetime frontier. An 80-year lifetime could include a long cruise to Saturn, a multi-year tour of its moons, and even a slow drift outward beyond Neptune. But to understand the true limit, you need to understand what sets the pace. In space, most of the journey is coasting. If you want to go farther, you need to leave the solar system faster. The speed required to escape the Sun's gravity from Earth's orbit is about 42 kilometers per second. That is the solar escape speed at Earth's distance. Most missions do not reach that speed directly. They reach a lower speed and then use gravity assists or long thrust phases. If you could build a ship that left Earth orbit and accelerated continuously at a small rate, you could reach much higher speeds. Even a tiny acceleration held for years becomes transformative. Consider an acceleration of 1 millimeter per second squared. That is about 1/10,000th of Earth's gravity. You would barely feel it. Over 1 year, it adds about 31.5 kilometers per second. Over 10 years, about 315 kilometers per second. Over 30 years, about 945 kilometers per second. That is almost 1,000 kilometers per second, which is about 0.3% of the speed of light. At 0.3% of light speed, you travel 1 light year in about 333 years. That is still beyond a single lifetime. But you could travel far in the solar system. You could cross from the Sun to the Kuiper Belt in months. You could reach the inner Oort cloud in decades. This is the scale where the solar system becomes less like a city and more like a continent. The distances are still huge, but time begins to bend. Now consider a higher acceleration, like 1/100th of a g. That is about 0.0098 meters per second squared. It is gentle but noticeable. Over 1 year, it adds about 300 kilometers per second, which is about 1% of the speed of light. If you could keep that up for years, you would reach relativistic speeds. The problem is energy. Acceleration is not free. It requires propellant, or it requires pushing against something external. Rockets carry their reaction mass. That mass grows rapidly as you increase your desired speed. The rocket equation is the quiet rule that haunts all propulsion. It says that to increase your velocity by a certain amount, you must expel propellant at high speed, and the mass ratio grows exponentially. For chemical rockets, exhaust speeds are only a few kilometers per second. For nuclear thermal rockets, maybe around 9 kilometers per second. For electric propulsion, exhaust speeds can be tens of kilometers per second. For fusion, maybe much higher. But even then, large delta V demands huge propellant fractions. So when we ask how far we could travel in a lifetime, we are also asking what propulsion we can build that escapes the rocket equation's worst penalty. One path is to carry a lot of propellant and accept that the ship is mostly fuel. This could work for unmanned probes. It is difficult for humans. Another path is to use external propulsion. A sail pushed by light does not need to carry propellant. Instead, it rides pressure from photons. Solar sails can be pushed by sunlight. They provide small acceleration. Over years, they can reach high speeds. But the acceleration drops with distance from the sun. A more ambitious version is a laser sail. A powerful laser array near Earth or near the sun shines on a small, reflective sail. The beam provides thrust. If the laser is strong enough, the sail can reach a significant fraction of light speed. Projects like Breakthrough Starshot imagine gram-scale probes that could reach Alpha Centauri in about 20 years. That is for tiny payloads, not humans. But it tells you something important. If you do not have to carry propellant, the reachable distance within a lifetime expands dramatically. For humans, a laser sail is harder. The sail must be huge. The beam must be controlled for long periods. The ship must survive intense heating and acceleration. Still, even if human laser sails are not near, the concept changes our map. It suggests that for small payloads, interstellar distances can be lifetime distances. But the question we began with is about a person. So we return to human experience. Inside one lifetime, a person could in principle travel to Mars, live there, and return. A person could travel to the asteroids. A person could travel to Jupiter's moons. A person could travel to Saturn and live in orbit around Titan or Enceladus. These are not easy missions, but they are within reach of known physics and plausible engineering. The limit might be set more by biology and politics than by propulsion. Radiation exposure is one of the harshest constraints. Outside Earth's magnetosphere, cosmic rays and solar storms can damage DNA and raise cancer risk. The longer you spend in deep space, the higher the dose. To travel far and stay healthy, you need shielding. Shielding can be passive, like thick layers of water, plastic, or regolith. Or it can be active, like magnetic fields, though active shielding is complex. Water is a useful shield because you need it anyway. A habitat surrounded by water tanks can reduce radiation, but the mass is large. If you build a ship for a decades-long journey, you might also build it with rotation to provide artificial gravity. Microgravity causes muscle loss, bone loss, and other changes. People can adapt, but long missions benefit from gravity. A rotating habitat can provide gravity through centripetal acceleration. The radius must be large enough that the rotation rate is comfortable. If the radius is too small, the Coriolis effects can cause dizziness. All of this adds mass and complexity, but it does not break physics. Now we widen the view. What about traveling to another star in one lifetime? The nearest star system is Alpha Centauri, about 4.37 light-years away. At Voyager speeds, the trip would take tens of thousands of years. To do it in 80 years, as measured by Earth, you would need an average speed of about 5.5% of the speed of light. That is around 16,500 kilometers per second. That number is enormous compared to chemical rockets. It is enormous compared to nuclear thermal. It is even enormous compared to most electric propulsion. You can reach that speed with a light sail or with a fusion rocket in theory, but the engineering is extreme. If you aim for 1/10 of light speed, the trip to Alpha Centauri would take about 44 years, plus time to accelerate and decelerate. That is within a lifetime, but it assumes you can build a ship that can push itself to 0.1 C and then slow down. Deceleration is a hidden cost. Many interstellar concepts focus on acceleration because it is the exciting part. But if you want to arrive and not just fly through, you must slow down. That often requires as much energy as speeding up. A ship could decelerate by carrying propellant, by using magnetic sails that push against the interstellar medium, or by using a laser array at the destination, which is unlikely. A magnetic sail is an interesting idea. A large magnetic field can deflect charged particles in space, creating drag. The interstellar medium is thin, but at high speeds, even thin matter can provide force. It would be a long, gradual braking process. Another method is to use a photon sail and a beam from behind, but the beam must follow the ship for years. So, for a human ship, a realistic interstellar mission in one lifetime is not impossible in principle, but it requires a civilization-level project. Yet there is a twist. The lifetime we measure is not the same in all frames. If you travel close to the speed of light, time dilation becomes meaningful. In the traveler's frame, less time passes than on Earth. For example, at 0.8 C, the time dilation factor is about 1.67. That means 1 year on the ship is about 1.67 years on Earth. At 0.9 C, the factor is about 2.29. At 0.99 C, it is about 7.09. At 0.999 C, it is about 22.4. So if you could reach 0.99 C, a trip of several light years might take only a few years of ship time, though decades would pass on Earth. This is where the phrase lifetime becomes ambiguous. A traveler could reach a distant star cluster within their lifetime as experienced on the ship, but not within the lifetime of people on Earth. However, reaching 0.999c is vastly harder than reaching 0.1c. The energy grows without bound as you approach light speed. For a given mass, the kinetic energy at relativistic speeds is enormous. At 0.1c, the kinetic energy is about 0.5% of mc squared. At 0.9c, it is about 1.29 mc squared. That is more than the mass energy of the ship. That is a staggering requirement. It also creates another danger: collisions. At high speeds, even a tiny dust grain carries huge kinetic energy. A grain of sand at 0.1c is like an explosive. At 0.9c, it is catastrophic. A ship traveling at relativistic speeds must have shielding or a way to clear its path. This could be a forward plasma field, a sacrificial shield, or a laser system that vaporizes dust ahead. But again, complexity grows. So, what distance is realistic for a person in one lifetime with plausible future technology, not civilization-spanning miracles? A reasonable answer is the outer solar system. A person might reach Jupiter and Saturn and spend years exploring their moons. A person might reach the Kuiper Belt and see objects like Pluto, Eris, and others at close range. A person might travel beyond Neptune and see the Sun as just another bright star. In that zone, the travel times are long, but not absurd. The engineering is hard, but not impossible. The hazards are serious, but manageable, with shielding and planning. If you widen the timeline to include a generation ship, the picture changes. A generation ship is a ship that carries people who will live and die on board, and whose descendants will arrive. In that case, the lifetime is not one person's life, but a chain. Still, for the people on board, it is their entire world. A lifetime could be lived between stars, never arriving. Generation ships solve the problem of time, but they create problems of society, ethics, and reliability. A smaller version is a sleeper ship, where passengers are in suspended animation or deep sleep. True suspended animation is not yet possible for humans, but it is often discussed. If it were possible, it would allow interstellar travel at lower speeds, because the psychological burden is reduced. But the physics of propulsion does not change. So far, we have talked about travel as a straight line outward. But within a lifetime, there is another kind of travel that goes far without leaving the solar system quickly. It is the travel of perspective. A person might not reach another star, but they could still experience deep time by observing distant objects. A telescope in deep space could see exoplanets with less interference. A mission to the outer solar system could place instruments far from the sun's glare. In that sense, the farthest you travel in a lifetime might be the farthest you see. But Raphael asked for a concrete record, so we stay concrete. Let us map the solar system journey distances in time. To the moon, about 3 days. To Mars, about 6 to 9 months with current methods. Shorter with higher energy trajectories. To Jupiter, a few years with traditional paths. Potentially under 2 years with higher energy and better propulsion. To Saturn, 6 to 8 years for many robotic missions. But a crewed mission could be faster if it carries more energy. To Uranus, a decade or more with chemical and gravity assists. To Neptune, more than a decade. To Pluto, about 9.5 years for New Horizons. To 100 astronomical units, about 15 to 20 years at New Horizons or Voyager-like speeds. to 1,000 astronomical units, centuries at those speeds. So a lifetime could reach beyond 100 astronomical units if the ship is fast and durable. What is at 100 astronomical units? The heliosphere begins to thin. The solar wind is weaker. The background of interstellar space begins to dominate. Beyond that, at thousands of astronomical units, the Oort cloud begins. That region is likely filled with icy bodies, a vast reservoir of comets. In a strict sense, reaching the Oort cloud in one lifetime requires much higher speeds than current probes, but it is still within the solar system. If you could reach 1,000 kilometers per second, you could reach 1,000 astronomical units in about 4.7 years. That speed is 0.0033 c. It is far beyond current chemical rockets, but perhaps not beyond far future electric or nuclear propulsion. So in a far future scenario, a person could see the inner Oort cloud within a lifetime. Now consider what the sky looks like out there. Near Earth, the sun is a disk. It casts sharp shadows. The stars are points. Near Saturn, the sun is still bright, but smaller. The stars are sharper in the black. Beyond Neptune, the sun becomes a bright star. The inner planets are lost. At 100 astronomical units, the sun is still the brightest thing in the sky, but it is not blinding in the same way. It is like a very bright star. You could look toward it with caution. The cosmic microwave background is still invisible to eyes, but your instruments see it. At these distances, the idea of home changes. The radio delay becomes hours. Real-time conversation is gone. The ship becomes the only immediate world. So the psychological side becomes as important as the propulsion. A ship for a lifetime journey must not only survive, it must remain a place where a person can live. That means a stable environment, a rhythm, a sense of purpose. It also means handling isolation. In our time, isolation is often measured in days or months. A lifetime journey is measured in decades. That is why many realistic long missions are framed as explorations of nearby worlds, where there is at least a destination and a clear operational plan. So, perhaps the best answer to our question is not a single number. It is a set of regimes. Regime 1, near term, within known technology. A lifetime can reach Mars and the inner asteroids. With serious effort, it can reach Jupiter and Saturn. Regime 2, medium future, with advanced nuclear electric propulsion and large ships. A lifetime can tour the outer planets, reach the Kuiper Belt, and perhaps go beyond 100 astronomical units. Regime 3, far future, with external propulsion or very high performance engines. A lifetime could reach the inner Oort cloud, and small probes could reach nearby stars. Regime 4, extreme future, with relativistic travel. A lifetime as experienced by the traveler could reach many stars, but at enormous energy and risk. In each regime, the line between human travel and machine travel matters. A machine can travel farther because it does not need air and water. It can sleep for decades. It can be hardened against radiation. A human wants comfort, safety, and return. Now we move from distance to the concept of lifetime again. If you spend your life traveling, what does that mean? Do you depart and never return? Do you return to a world that has changed? Even a trip to Mars changes your timeline. You might return years later. Your friends have aged. The world has moved. A trip to Saturn might mean you return decades later. You might return old. A trip beyond Neptune might mean you never return, not because you cannot, but because the time is too large. So a lifetime journey is also a choice. In this record, we treat it as a thought experiment. But the human heart is not an equation. Now we address one more deep idea. The distance you can travel depends on what you are willing to sacrifice. If you do not require return, you can spend your propellant budget on acceleration and accept a flyby. If you require return, you must plan for deceleration, and often for a second acceleration. Return doubles your energy cost, so the reachable distance within a lifetime is larger for one-way missions. One-way missions also align with the idea of migration. Human expansion through history has often been one way. People leave and do not return. In space, one-way missions are more plausible for far targets. That means that within a lifetime, a person might travel farther by choosing not to come back. Now let us bring this back to a simple image. Imagine a person leaving Earth, passing the moon, seeing Earth shrink and then moving outward. The sun becomes smaller. The planets become points. The ship's windows show a dark sky with scattered stars. At Jupiter, the planet fills the sky, a banded world with storms. At Saturn, the rings are a plain of ice and light. At Uranus and Neptune, the worlds are cold and distant. Beyond them, the ship passes through the Kuiper Belt, past small worlds and frozen debris. And then, slowly, the ship enters a region where the sun is only one bright star among others. That is the far edge of the solar system. In a lifetime, a person could reach that edge if the ship is fast enough, and if the mission is built to last. What does fast enough mean? Let us choose a target. Suppose you want to reach 200 astronomical units in 60 years of travel time, leaving 20 years for preparation and exploration. 200 astronomical units is about 30 billion kilometers. Over 60 years, that is about 0.5 billion kilometers per year. That is about 16 kilometers per second. That is within the range of fast probes. It is not within the range of current crewed ships, but it is not a relativistic number. So, for a one-way mission, a human could reach several hundred astronomical units within a lifetime if the ship could maintain a cruise speed of tens of kilometers per second. That might be achievable with nuclear electric propulsion, gravitational assists, and a long period of thrust. If you want to reach 1,000 astronomical units within a lifetime, you need around 80 kilometers per second average, depending on time budget. That is still not relativistic, but it is challenging. If you want to reach 10,000 astronomical units, you need hundreds of kilometers per second. That begins to require more exotic methods. So we see a gradient. Within the solar system, the distances are large, but not insane. Between stars, the distances become the true barrier. Now we address one last piece, the speed limit imposed by humans themselves. A human body can tolerate acceleration. 1 g is comfortable and familiar. 1/10 of a g is comfortable over long periods. Higher accelerations can be tolerated for short times, but are stressful. If you had a ship that could accelerate at 1 g for half the trip and decelerate at 1 g for the second half, you could reach almost any place in the galaxy within a human lifetime as experienced on the ship, because time dilation would become extreme as you approach light speed. This is a famous result in relativity, but it is not a practical plan because the energy is astronomical. Still, it shows that physics does not forbid long-distance travel within a lifetime in principle. It forbids it only in practice with our current means. So, what is the honest conclusion? In the next century, a person might realistically travel to Mars, to the asteroids, and perhaps to the moons of Jupiter and Saturn. In a more advanced era, a person might travel to the Kuiper Belt and beyond, living out decades in the black. Interstellar travel within one lifetime is likely to remain the domain of small probes first. And if humans ever do it, it will be a long, deliberate project built by many people so that a few can go. This is not a small thought. A lifetime is long enough to cross oceans, build cities, raise children, and change a world. In space, a lifetime is long enough to reach the outer neighborhood of the sun, and for now, that is already an enormous horizon. As the record continues, we slow down and fill in the missing distances. The reason is simple. Most people do not think in kilometers when they imagine space. They think in pictures. A rocket, a planet, a bright star. But a lifetime journey is not a picture. It is a schedule. It is fuel. It is maintenance. It is what you eat, what you breathe, and what you do at 3 a.m. on year 17, when nothing outside the window looks different. So we go step by step. First, we build a scale that fits inside a mind. A useful starting point is light time. Light is fast enough that it sets the limit for how quickly information can move. It also gives you a natural ruler. The moon is about 1.3 light seconds away. Mars, when it is closest, is about 3 light minutes away. When it is farthest, it is more like 22 light minutes. Jupiter is around 35 to 50 light minutes away. Saturn is around 70 to 90 light minutes away. Neptune is around 4 light hours away. Pluto can be more than 5 light hours away. The edge of the heliosphere, where the solar wind meets the interstellar medium, is on the order of 12 to 20 light hours away, depending on direction and how you define the boundary. Alpha Centauri is more than 4 light years away. That is a very different kind of distance. It is not a larger number of hours. It is a larger kind of time. Now we translate light time into travel time. A common cruise speed for interplanetary probes after leaving Earth is around 10 to 20 kilometers per second relative to the Sun, sometimes higher. New Horizons left Earth on a high-energy trajectory and reached roughly 16 kilometers per second relative to the Sun. Voyager 1 is moving around 17 kilometers per second relative to the Sun. At 17 kilometers per second, you travel about 1 astronomical unit in roughly 102 days. That means you could cross the distance from Earth to the Sun in about 3 months. If you were already moving at that speed, and if you did not need to slow down. It also means you could reach Jupiter's orbit around 5 astronomical units in about a year and a half, again ignoring the details of launch and trajectory. So why do missions to Jupiter often take years? Because the ship is not launched at full cruise speed relative to the Sun. It is launched from Earth, which is already moving around the Sun at about 30 kilometers per second, and the ship must shape its orbit with limited energy. It must also aim for a moving target. If you have a ship that can add energy after launch, the timeline compresses. That brings us to propulsion again, but now we treat it like a menu. Chemical propulsion is a sprint. Nuclear thermal propulsion is a stronger sprint with better efficiency. Electric propulsion is a slow walk that never stops. Fusion propulsion is a dream that might become a steady run. And beam-driven sails are a push from behind, a push so strong that you can leave the solar system without carrying the fuel that would normally fill your ship. For a lifetime journey, the slow walk matters more than the sprint. If you can accelerate gently for years, you can build speed without an absurd mass ratio, but you still need propellant for most rocket types. The most honest way to compare these systems is not by their names, but by two numbers. One is exhaust velocity, how fast the engine throws mass out the back. The other is power, how much energy you can turn into thrust over time. Chemical rockets have high thrust but low exhaust velocity. Electric engines have low thrust but high exhaust velocity. If you could build an electric engine with very high power, you could get both. So imagine a ship with a nuclear reactor that produces tens of megawatts or more. That is a small power plant by human standards, but a large one for space. If it drives an electric thruster for years, it can change the entire mission. You might still not reach another star, but you can reach the places in the solar system that are now only reached by probes. In a lifetime, you can become the probe. Now we shift from propulsion to the environment of space. Space is not empty. It is thin, but it is not nothing. There are particles, dust, fields, and radiation. For slow ships in the solar system, dust is mostly a navigation and erosion problem. For fast ships, dust becomes a weapon. Even at tens of kilometers per second, a collision with a small grain can damage exposed surfaces. At hundreds of kilometers per second, it becomes dangerous. At a fraction of light speed, it becomes catastrophic. So there is a practical ceiling on speed for unshielded craft. For a crewed ship, you would likely accept a speed that is high but not extreme, because shielding has a cost. This is one reason why the outer solar system is a more likely lifetime frontier than the stars. The speeds required are high, but not in the regime where a single grain is a disaster. Now we set up a few example journeys, each one designed to fit inside a lifetime. Journey 1. The inner system loop. A person leaves Earth, travels to the Moon, then to a near-Earth asteroid, then to Mars, then back. This is a mission measured in years, not decades. It is a lifetime journey, only in the sense that it is one long chapter of a life. It is also the most realistic path for near-term crewed exploration. The main constraints are life support reliability, radiation, and the psychological challenge of being away from Earth for long periods. Journey 2. The Jupiter system. A ship travels to Jupiter and spends years there. Jupiter has moons that are worlds in their own right. Europa may have an ocean. Ganymede has a magnetic field. Callisto is heavily cratered and stable. A human in orbit around Jupiter must contend with radiation belts, which are intense. So the ship might spend time around the less intense regions, or around a moon with some shielding. A mission like this could last a decade or more. A person could leave in their 20s and return in their 30s. Or they could leave and never return, choosing to build a life in the Jupiter system. Journey 3. Saturn and Titan. Titan is one of the most interesting targets for a lifetime mission because it has a thick atmosphere, lakes of hydrocarbons, and a surface pressure similar to Earth. It is cold, but it is stable. A human could imagine living in habitats there. A mission to Saturn, with time to explore and return, could be measured in decades. It could be a lifetime mission in the sense that it takes the prime of a life. Journey 4. Outward to the Kuiper Belt. This is the first journey that feels like leaving. The Kuiper Belt is not a single place. It is a region of space beyond Neptune, filled with icy bodies. Many are small, some are large. Pluto is a dwarf planet with a thin atmosphere, mountains of ice, and a complex surface. Eris is farther out. Makemake and Haumea and others mark the region. A ship that reaches this zone within a lifetime must either be fast or accept that most of the life is spent coasting. So you might design the mission as a one-way journey. You leave Earth, you travel outward, you visit a handful of objects, you continue outward. The ship becomes an observatory, the crew becomes a small society. In this scenario, a person might reach 50 or 100 astronomical units within their lifetime and spend years in that outer region. Journey 5. The heliopause. The heliopause is where the solar wind is stopped by the interstellar medium. It is not a wall, it is a transition. It is a boundary where the sun's influence becomes weaker. If you cross it, you are still near the sun by human intuition, but you are outside the bubble of the solar wind. The stars do not change, but the instruments see a new environment. A person who reaches this boundary would be living in a place no human has ever been. At Voyager speeds, it takes decades, so a lifetime mission could reach it. The challenge is not only travel time, it is endurance. A ship must remain functional for decades. That means redundancy. It means repair. It means a supply chain that is closed. For food, you either carry it or you grow it. Carrying decades of food is heavy. Growing food requires water, light, and management. So a lifetime ship is likely to be a small ecosystem. This has been studied in closed ecological systems on Earth, and it is hard. But again, it is not forbidden. Now we talk about a hidden limit: heat. In deep space, you can cool by radiating heat away. But if you have a powerful reactor, you must dump waste heat. That requires radiators. Radiators are large, delicate surfaces. They can be damaged by micrometeoroids. So high-power propulsion has a vulnerability. A lifetime ship must manage its power and its radiators carefully. Now we return to the stars, not to claim we can reach them, but to measure how far they are. A light year is about 9.46 trillion kilometers. At 17 kilometers per second, you travel about 0.057 light years per year. That means one light year takes about 7,600 years. Alpha Centauri would take about 77,000 years. So at present-day probe speeds, the stars are not lifetime distances. They are civilization distances. But the thought experiment becomes useful when we ask what speed would make them lifetime distances. If you want to reach Alpha Centauri in 80 years of Earth time, you need about 0.00555 C. If you want to reach it in 40 years, you need about 0.11 C. If you want to reach it in 20 years, you need about 0.22 C. Each of those steps is not linear in difficulty, it is closer to exponential, because the energy cost rises with the square of speed in the non-relativistic regime, and even faster in the relativistic regime. So most realistic interstellar concepts aim for small payloads. They accept that humans will not go first. That is a sober point. A lifetime journey for a person is likely to remain within the solar system for a long time. But within the solar system, there is still enough distance to spend a life. Now we add a set of simple lifetime rulers. Ruler 1, 1 kilometer per second. At 1 kilometer per second, you travel about 31.5 million kilometers per year. That is about 0.21 astronomical units, so 1 kilometer per second is slow for interplanetary travel. Ruler 2, 10 kilometers per second. At 10 kilometers per second, you travel about 2.1 astronomical units per year. Ruler 3, 20 kilometers per second. At 20 kilometers per second, you travel about 4.2 astronomical units per year. Ruler 4, 50 kilometers per second. At 50 kilometers per second, you travel about 10.5 astronomical units per year. Ruler 5, 100 kilometers per second. At 100 kilometers per second, you travel about 21 astronomical units per year. At that speed, you can cross from the inner solar system to Neptune in a little over a year. You can reach 100 astronomical units in under 5 years. You can reach 1,000 astronomical units in under 50 years. Now we see a new horizon. At 100 kilometers per second, the inner Oort cloud becomes a lifetime distance. So the question becomes, can a crewed ship reach 100 kilometers per second and sustain itself? It is hard, but it might be possible with nuclear electric propulsion over long durations, combined with gravity assists and a deep space staging. If you build a ship that departs from a high-energy orbit, perhaps close to the sun, and uses a powerful engine for years, you can push outward. This is not a launch from Earth like Apollo. It is a construction project. You build the ship in space. You fuel it in space. You depart from space. That is likely the only way. Now we address the second half of the title. In a lifetime. A lifetime is not only years, it is also how much risk you accept. A risky mission can go farther, because it can accept thinner shielding, fewer redundancies, and one-way travel. A safe mission is heavier and slower, so there is a trade. If you want to maximize distance, you accept risk. If you want to maximize safety, you accept a smaller horizon. Most human programs choose safety, even if the risk remains. So the likely human lifetime frontier remains the planets. But the record asked how far we could travel, not how far we will. So we allow ourselves one more step into the plausible future. Imagine a ship that can provide artificial gravity, radiation shielding, and reliable life support. It has a nuclear reactor. It has electric propulsion. It accelerates slowly for years. It reaches 50 kilometers per second. It passes the outer planets. It reaches 500 astronomical units. In that journey, the sun becomes an ordinary star. The night sky is nearly the same, but the direction of the sun is no longer a bright center. Communication becomes a delay measured in days, and the ship, by necessity, becomes self-contained. In that scenario, a person could travel farther than any human has ever traveled, and still remain within a single lifetime. This is the honest frontier of a lifetime, not another star, a long path outward, away from the warm inner region. Now we add the last missing layer, the one that is easy to say and hard to feel: time dilation. When people hear about time dilation, they often think it is a shortcut to the stars. In one sense, it is. If you could travel close to the speed of light, you could cross many light years, while only a few years pass for you. But time dilation does not remove the need for energy. It does not remove the need for shielding. It does not remove the problem of hitting dust at a speed where dust becomes a bomb. So we treat it as a separate chapter in the same question. How far could a person travel in a lifetime, measured in their own time, if they could travel very fast? To answer, we need a simple way to talk about speed. The speed of light is about 300,000 kilometers per second. At 10% of light speed, you travel 0.1 light years per year, ignoring acceleration and deceleration. At 50% of light speed, you travel 0.5 light years per year. At 90% of light speed, you travel 0.9 light years per year. So at 0.5 c, Alpha Centauri is under 9 years away, as measured by Earth clocks plus the acceleration time. But as measured by the traveler, it is shorter. The time dilation factor at 0.5 c is about 1.15. That is not a huge difference. At 0.9 c, the time dilation factor is about 2.29. At 0.99 c, it is about 7.09. So to get the dramatic lifetime effect, you need to go very fast. Now imagine a ship that can accelerate at 1g. 1g is about 9.81 meters per second squared. If you accelerate at 1g for 1 year, your speed would exceed the speed of light in a naive calculation. But relativity prevents that. Instead, your speed approaches light speed asymptotically. In a 1g ship, you can reach 0.77c in about 1 year of ship time. In 2 years, you can get closer. This is the famous idea that with constant acceleration, you can reach almost anywhere, at least in principle, within a lifetime. But the energy requirement is so large that it becomes hard to treat as a practical plan. Still, it is useful as a ruler. It tells you that the ultimate limit is not distance. It is the ability to build a ship that can sustain high acceleration and survive the environment at high speed. If you cannot do that, then time dilation is not your tool. So, for the realistic lifetime frontier, time dilation is mostly a story about probes. A small probe with a sail might reach 0.2c. A larger probe might reach 0.05c. Those speeds could allow missions to nearby stars within a human lifetime of Earth time. But the human rider is still the hard part. So we return to the human case. A person can spend a lifetime traveling within the solar system, not because the solar system is small, but because the work of getting there and staying alive is long. A person can also spend a lifetime on a mission that is mostly waiting. That waiting is not an empty thing. It is routine. It is repairs. It is monitoring. It is exercise. It is meals. It is the knowledge that outside the hull there is no air, no sound, and no easy rescue. So a lifetime journey is not only a line on a chart, it is a lived environment. This is why long missions in space often become more like voyages across an ocean than like trips across a desert. The ship is the world. The crew is the society. The destination is important, but the path is the main reality. Now we add a final set of distances that are not about planets, but about the shape of our neighborhood. The solar system is moving through the galaxy. The sun orbits the center of the Milky Way at about 220 kilometers per second. If you were able to match the sun's motion and then add or subtract speed, you could in principle shape a trajectory relative to the galaxy. But that is not a near-term plan. Still, it helps to remember that a lifetime of travel does not happen in a still universe. Even if you did nothing, the sun would move through space. In one human lifetime, the sun travels a vast distance around the galaxy, but you do not feel it because you are moving with it. A traveler who leaves the solar system is stepping out of that shared motion. Now we return to the practical question one last time. If you asked for one number, one honest number, for how far a person could travel in space in a lifetime with plausible future engineering, the answer is this. A person could reach the outer planets and live to see them. A person could reach the Kuiper Belt. A person could cross hundreds of astronomical units. And if the ship is built as a closed ecosystem with high reliability and long thrust, a person could reach the far edge of the sun's influence. That is already far enough that the sun is a star, and Earth is not a place on a map, but a direction. Before we close, we answer a quieter question that hides inside the main one. What does travel mean if you cannot land? In much of space travel, you do not step onto a surface. You pass by, you orbit, you map, you listen to fields and particles. You take photographs that are made of numbers. So a lifetime journey might not be a flag on a world. It might be a long collection of observations, taken as the ship crosses different regions. In the inner solar system, you see sunlight and solar storms. In the asteroid belt, you see debris and small bodies. Near Jupiter, you see radiation and magnetospheres. Near Saturn, you see rings and moons. Beyond Neptune, you see the slow, cold drift of icy objects. And beyond the heliopause, you see a different plasma environment and a different kind of background radiation. A lifetime ship could become an outward-moving laboratory. That changes how you think about distance. It is not only where you arrive, it is what you pass through. Now we add a final practical detail, because it often decides the difference between a plan and a fantasy. Communication. At Mars, you can talk with a delay measured in minutes. At Jupiter, the delay is close to an hour. At Neptune, the delay is hours. At 100 astronomical units, the delay is about 14 hours. At 500 astronomical units, it is about 70 hours. So within a lifetime, you can easily reach a point where there is no real-time guidance. The crew becomes fully autonomous. The ship must be able to diagnose itself and fix itself. This is why long missions push toward automation and towards systems that can be serviced. It is also why, for a long outward journey, the crew's skills matter as much as the engine. A lifetime crew is not only passengers, they are engineers, farmers, doctors, and mechanics. They are also historians, because the mission itself becomes a culture. The ship will have years that feel ordinary. It will have days that feel dangerous. It will have long periods where the only change is the slow shift of the sun against the stars. We also add one more constraint that decides whether a long journey is comfortable or brutal. Mass. Every kilogram you bring must be launched or gathered in space. If you bring thick radiation shielding, you pay in launch mass. If you bring spinning habitats, you pay in structure. If you bring a reactor, you pay in radiators. If you bring a farm, you pay in volume, water, and complexity. So a lifetime ship is always an argument about priorities. One design might be small and fast, with a tiny crew and limited comfort, aiming to reach far distances quickly. Another might be large and slow, with a larger crew and better living space, aiming to survive the long cruise. The first design maximizes distance. The second design maximizes life. Both are legitimate answers to the same question. Now imagine that you are building the mission with a fixed lifetime budget. You do not only spend propellant, you spend attention. Every extra system is something that can fail. Every extra capability is something that must be tested and maintained. So even with advanced propulsion, the most reliable way to go far might be to go simple. That is why many deep space plans begin with robots. Robots tolerate simple lives. Humans do not. So the farthest distance in a lifetime might not be the farthest distance physics allows. It might be the farthest distance a crew can remain healthy, safe, and focused. It might be the farthest distance where the ship can still be repaired with the tools on board. It might be the farthest distance where the crew can still look out and feel that the journey has a shape. In that sense, the solar system is not a small place. It is a complete world of distances. You can spend an entire life moving through it and still leave parts unseen. Now we close the record in the simplest way, but we leave a final image in the mind. Picture the ship late in the journey. The interior lights are soft. The air is clean. The sound is fans and pumps and quiet conversation. A clock marks the years since departure. The crew knows the routines so well that they can do them half asleep. Outside, the sun is no longer a disk. It is a star with a direction. The constellations are almost unchanged, but careful measurements show parallax, small shifts caused by distance. The nearest stars separate slightly from each other, like a drawing that is slowly being pulled apart. The radio messages from Earth arrive as recordings. Replies are sent as recordings. The crew has learned to plan weeks ahead because a mistake takes days to correct. If the mission passes a Kuiper Belt object, it is not a quick flyby in a slideshow. It is a real approach. The object grows slowly in the window. Its shape becomes clear. Its surface shows scars and layers and bright ice. A person can look at it and know they are seeing something that no one on Earth has ever seen directly. That is the true meaning of a lifetime journey. It is not a single heroic moment. It is a long chain of ordinary days that carry you into a place that is not home. If you measure distance by where humans can go today, a lifetime reaches the moon. Even that short distance carries a lesson. The moon is close enough that you can return in a week, but far enough that you must bring everything that matters: air, water, power, shelter, tools, spare parts, a way to handle sickness, a way to handle a fire, a way to handle a leak. So when you scale the distance up, the problem does not only grow, it changes shape. At Mars, the delay makes remote help slow. At Jupiter, the radiation makes shielding essential. At Saturn, the time makes the ship itself the primary habitat. A lifetime journey is not only a propulsion question, it is a systems question. It is a human factors question. It is an endurance question. If you measure by what we could build with near-future engineering, a lifetime reaches Mars, the asteroids, and the moons of the outer planets. If you measure by what might be possible with advanced propulsion, a lifetime could reach the far edge of the solar system, and perhaps the first hint of the Oort cloud. In that far edge scenario, the ship does not travel as a tourist. It travels like a lighthouse. It carries a set of instruments that watch the sun from far away, measure the interstellar medium, and map the faint objects that never come close to the inner planets. The crew's work would be slow and careful. They would time their observations. They would plan their course years ahead. They would treat every repair as a serious event, because replacing a failed part is not a call away. It would be exploration in the most literal sense. You would be outside the familiar bubble of the sun. You would be moving through a different kind of space. There is also a softer reward. Far from the sun, the sky becomes a deeper kind of dark. The glare is lower. The faint structure of the Milky Way is sharper. If the ship carries a good telescope, the crew could watch nearby stars with a clarity that is hard to get from inside the inner solar system. So even without reaching another star, a lifetime journey outward changes what you can know. It changes what you can measure, because the noise of the inner solar system falls away. It changes what you can see, because the sun is no longer a floodlight in the corner of every image. And it changes what you can feel, because home becomes a direction instead of a place. It changes the meaning of distance itself. And if you measure distance by the traveler, not by Earth, then the farthest distance is hidden inside the speed of light itself, waiting behind an engineering challenge so large that it becomes a story about civilizations. This was a quiet archive story, where the story ends sleep begins.